Remember that if we take a homogeneous linear second-order differential equation and divide up everything by the leading coefficient a sub 2x, we can write this guy in standard form. In standard form, you get the second derivative of y plus pxy prime plus qxy equal to 0. Px is a1 divided by a2, and qx is a0 divided by a2. And then we can take the solutions of a sub 2 and define ordinary and singular points. A point x sub 0 is said to be an ordinary point of a differential equation if px and qx are both analytic at x sub 0. Otherwise, we say that x sub 0 is a singular point. We can divide up and classify singular points into different categories as well. So again, let us rewrite everything. A singular point x sub 0 of a linear differential equation of the form a sub 2x y double prime plus a1x y prime plus a sub 0 xy equal to 0 if we write this as standard form of the second derivative of y plus pxy prime plus qxy equal to 0 is called regular singular point if you multiply px by the linear factor x minus x sub 0 and take qx and multiply it by the quadratic factor, both of them become analytic at x sub 0, or the limit exists. Otherwise, we call it an irregular singular point. Let's take a look at a few examples to feel comfortable about this topic. In the differential equation x squared minus 4 to power 2 times the second derivative of y plus 3 times x minus 2 y prime plus 5y equal to 0, basically 2 and negative 2 are the solutions of taking the leading coefficient and set it equal to 0. If we divide everything by the leading coefficient and reducing the coefficient to lowest terms, you can basically write this differential equation in standard form. The second derivative of y plus 3x minus 2 divided by x squared minus 4 to power 2 y prime plus 5y divided by the leading coefficient, which is x squared minus 4 to power 2. We can write down the denominators in simpler form. Remember that x squared minus 4 is x minus 2 times x plus 2, and then x squared minus 4 to power 2 becomes x minus 2 times x plus 2 to power 2, or basically x minus 2 to power 2 times x plus 2 to power 2. The denominator is 0 whenever you have x equals to 2 or x equals to negative 2. So we found the solutions for the leading coefficient down here. Now we need to classify these into singular points or in terms of regular and irregular singular points. Px can be further down, broken into smaller pieces, because we can get rid of the x minus 2 on the numerator and simplify the denominator to be x minus 2 times x plus 2 to power 2. And this guy, q of x, stay the same. 5 divided by x minus 2 to power 2 times x plus 2 to power 2. Now let us begin. We are following the definition of regular and irregular singular points. Let us test px and qx at each singular point. A singular point x equal to x sub 0 is a regular singular point if the following limit exists. First of all, if you multiply px by the linear factor x minus x sub 0 as x goes to 2 and x minus 2 to power 2 by qx as x goes to 2, these two limits exist. So x minus 2 times px, you get x minus 2 px, so you have x minus 2, px is, as we calculated, that is 3 times x minus 2 divided by x squared minus 4 to power 2, which can be simplified further into 3 times x minus 2 to power 2 divided by x squared minus 4 to power 2, or in simpler version, if you get rid of the common factor on the numerator and the denominator, it is just 3 divided by x plus 2 to power 2. You can easily find the limit as x goes to 2, while you're multiplying px by x minus 2, which is basically 3 divided by 2 plus 2 to power 2, or 3 over 16. So the limit exists. So far, we're good with our calculation. Now, you have to multiply qx by x minus 2 to power 2. So we need to check both px and qx for x equals to 2. We are rewriting our definition. A singular point is a regular singular point if both of these limits exist. We check that for px. Now we're going to check that for qx. Let's multiply qx by x minus 2 to power 2 and then take the limit. X minus 2 to power 2 times qx is x minus 2 to power 2, and qx, as you remember, is 5 divided by x squared minus 4 to power 2. Well, now we just simplify this into 5 divided by x plus 2 to power 2. If you take the limit as x goes to 2, this is basically 5 divided by 2 plus 2 to power 4, or 5 divided by 16. So the second limit exists. So what's the meaning of that? It means that x equals to 2 is a regular singular point. You can also write it this way. A function is analytic at a point if it can be represented as a convergent Taylor series around that point. Since function 3 divided by x plus 2 to power 2 and its derivatives are continuous at 2, we conclude that 3 divided by x plus 2 to power 2 is differentiable and smooth at x equals to 2, and it can be expressed as a Taylor series around 2. Therefore, 3 divided by x plus 2 to power 2 is analytic at 2. A function is analytic at a point if it can be represented as a convergent Taylor series around that point. It means that it is infinitely differentiable and its derivatives are continuous in a neighborhood around that point. And here, for x minus 2 to power 2 times qx, that we simplify to 5 divided by x plus 2 to power 2, x equals to 2 belongs to the domain of this function, and then you can easily take the derivative. The function is differentiable and it has continuous higher order derivatives. So for sure, you can say that, hey, 5 divided by x plus 2 to power 2 can be represented as a Taylor series around 2, meaning that this function is also analytic at x equals to 2. So I gave you two different explanations about these two be analytic at 2. Now let us move on to x equals to negative 2. Let us check x plus 2 times px and find the limit. X plus 2 times px can be simplified as 3 divided by x minus 2 times x plus 2. We're basically doing algebra. At x equals to negative 2, if you take the limit, you're going to see that since x approaches to negative 2 and you have x plus 2 as a factor on the denominator, you end up with a 0 on the denominator. So the limit doesn't exist while x approaches to negative 2. So it means that you have irregular singular point at negative 2. So again, x equals to negative 2 gives you irregular singular point for this example. Another example for you. X cubed times the second derivative of y plus 4x squared y prime plus 3y equal to 0. Let us write this guy in standard form by dividing everything by x cubed. So when you divide everything by the leading coefficient, which is x cubed, it becomes the second derivative of y plus 4 divided by xy prime plus 3 divided by x cubed y equal to 0. So this gives us the standard form of the second order differential equation. Px and qx are basically defined as 4 divided by x and 3 divided by x cubed. Now, if you take the limit of each one of these multiplying by the linear expression and the quadratic expression, you're going to see that the limits are going to be as follows. Then you can decide about being a regular singular point or irregular singular point. Take a look. To determine if you have a regular singular point, we need to find the limit of x times px as x goes to 0. When you multiply px by x, you get x times 4 over x, which is 4. This limit exists, so we don't have any issue with x times px. But if you take the limit of x squared times qx as x goes to 0, unfortunately, you end up with x on the denominator. When you're taking the limit as x goes to 0, this limit goes to infinity and the limit doesn't exist. So you can say that, hey, at x equal to 0, we have irregular singular point.